Hi everybody. This problem involves Newton's third law and friction between two objects that are sliding past one another. I'll give you the opportunity to pause now and read through the question. And since this is the internet, you can just pause and let's move on. So in this problem we have, well, really just friction that we care about, but each box experiences a force of friction. So Newton's third law comes into play because the frictional force caused by mass B on mass A will be the same as the frictional force caused by mass A on mass B, just in the opposite direction. I think it makes sense to start out on these problems by thinking conceptually like that. Now that we've got the basic idea that because of friction, mass A is going to slow down, and because of friction, mass B is going to speed up, let's draw free body diagrams for each of these. So we'll get this out of the way. And for mass A, we've got a force of gravity downward, which would be equal to the mass, which here was 5 kilograms, times 9.8 meters per second squared. So that's 49 newtons. And we've got a normal force, and I'm going to go ahead and label this force gravity A, and this one normal force A. And then that is moving to the right. And so the frictional force which opposes motion is going to point to the left. That is friction. Okay, now for mass B, we've got gravity downward, of course. Force of gravity on B. We've got a normal force upward. We also have an interaction with block A. So over on this diagram, we had a normal force upward on A. That was a force from block B acting on block A. So now we've got a force also from block A acting on block B. That's the Newton's third law thing. So that'd be Fn, let's see, I called that Fna earlier. There we go. Okay, and then this one, when we look at this picture again, mass A is going to be slowing down because of friction, so it's getting a force to the left due to friction caused by mass B. So mass B is going to get a force of friction caused by mass A that'll be in the opposite direction, to the right. So a frictional force over here. And I'll use the same variable as I did over on this side because, well, it's the same magnitude. Now, I'm interested in how these two accelerate. We can assume that they're going to accelerate only in the x direction. So what I really care about here is x acceleration and x forces. Now, on object B, I see I've got only one x force. Same goes for object A. But those are frictional forces. To find a frictional force, generally I'm going to use mu times normal force. And I see on object B, I've got I've got 3 forces in the y direction, including the normal force. Fna is the one I'd be interested in here. And on object A, I've only got 2 forces in the y direction, so hey, let's use that one. So here, I'll say net force in the y direction has to equal mass times acceleration in the y. We've got a normal force, A, upward, minus 49 newtons downward, is equal to, there's no acceleration in the y direction, so 0. So we got normal force A is just going to be equal to 49 newtons. Then I can find the frictional force by doing the force of friction is equal to mu times the normal force, which is, it was 0.3 in this problem, times 49 newtons. So our frictional force then is going to be 14.7 newtons. All right, now we need, let's see, acceleration, which is caused by only that frictional force. It's to the left for object A, it's to the right for object B, but those in both cases are the only forces in the horizontal direction. So back down here, I'm going to say my net force, and actually let me rewrite that here. my equation is acceleration in the x direction, is what I'm interested in, is equal to the net force in the x direction divided by the mass. I'm going to look at object A first, so I'll just add some A subscripts there to remind myself of that. Acceleration in the x direction for object A then is going to be 14.7 newtons. That was to the left, so I'll make that a negative. Divided by the mass of A, that was given as 5 kilograms. And so we get acceleration for object A is a negative 2.94 meters per second squared. For object B, we'll still have net force in the x direction divided by mass in the, no direction there, mass B. For this one, we've got the same force but in the opposite direction, so I'll make it a positive instead of a negative. And our mass here was given as 20 kilograms. So we'll get an acceleration for this one of 0.735 meters per second squared. And that's all there is to it. Keep in mind on problems like these, when we have two objects that are, let's pull this back up, when we have two objects that are moving relative to each other, it often won't be convenient to treat them as a system. And if we don't treat them as a system, if they're interacting, we should keep Newton's third law in mind, that any interaction they have results in two forces, one on each object, and those two forces are going to be equal in size and opposite in direction. Here we had two interactions. We had a normal force between the two, so they each got a normal force from the other one. For A, that was an upward force. For B, it was a downward force. And we had a frictional force. They each got a frictional force caused by the other one. For A, that was a force to the left. For B, it was a force to the right, but they were equal in magnitude. Newton's third law applies anytime we have two objects interacting with each other. Don't forget about it. And that's one of those things that may not be obvious, but can absolutely be essential to solving these problems. Thanks for watching. If you learned something, please go ahead and click like. If you think you might learn something from future videos, subscribe to this channel. And if you have any questions or comments, please leave those below. Thanks again. We'll see you soon.